Yeah, good evening everyone. So, my name is Anil Yadav and I am here to take the fifth tutorial on of fundamentals of semiconductor devices. So, can we start? Can you see my screen? Hello. Can anyone tell
Uh,
me? Yeah,
yeah, we're able to.
yeah, you can see my screen. Okay. So, in the last class, last tutorial we started the PN junction. Okay, I'll just briefly tell about the PN junction again, and we have covered. So, whosoever is new, so he or she won't feel left behind. So, in this one, so there is a P-type semiconductor here. This is the P-type semiconductor. Okay, let me just clear once this. Okay, I don't know why it is not clearing. Okay, it is I think it is saved, so that's why it is not clearing out. So okay, we have a p-type semiconductor here and n-type semiconductor. When we join them, what will happen is, so in p-type semiconductor there are impurities. Okay, so the impurities will ionize at the room temperature. They will ionize as uh, Na will change to Na minus plus whole H. Okay, this there will be abundance of holes. They are circling around in the semiconductor. Okay, and same is in the case of the n-type semiconductor. In n-type semiconductor, there are impurities with extra electrons. Okay, uh, pentavalent impurities, or here trivalent impurities. Okay, so in case of n-type semiconductor, these impurities will ionize as Nd to Nd plus electron. Okay, so when we join them, what will happen is, because of there is a abundance of holes in this side, p side, and there are abundance of electrons in the n side. So what will happen, because of the concentration gradient, so holes will flow from the p type to the n type, and electrons will flow from n region to the p region. So there is electron this because of the concentration gradient. If there is a flow of the charge carriers, what we call it as a diffusion. Okay, there is an electron diffusion from the n region to the p region, and there is a hole diffusion from the p region to the n region. Okay, so because of this diffusion, there will be because of this diffusion, so how long this diffusion can happen? So there will be a equilibrium state that will be reached. Okay, at equilibrium, what will happen is, so at equilibrium, what will happen is, because of electrons moving from the n region to the p region, so they will leave the ionized this immobile ion, this positive ion at the interface. And when hole move from the p region to the n region, uh, it will also leave behind the electron, this negative ion, that which is, these are the immobile ions. These are the immobile ions at the interface. Okay, so there will be a built-in electric field because of these ions from positive side, positive to negative ions. So there will be an electric field in the direction of from n region towards the p region. Okay, from this positive ions to the negative ion, so there will be an electric field in the minus x direction, we can say, in this case. Okay, so so this electric field, this built-in electric field, will prevent the movement of the further movement of the holes and the electrons. Okay, just give me a minute, someone wants to join. Okay, so we have already covered this. Okay, so at equilibrium, what will happen is the EF should be constant. Okay, EF should, at equilibrium, EF is constant, means there is no flow of the current. EF will be constant at that time. EF will be constant, because if there is a gradient in EF, as well. So there is a flow of current. But at equilibrium, we are saying it is equilibrium. So EF will be constant. EF means this Fermi level will be constant. So this is the P region. In the P region, okay, this is the kind of the bend. This is the bend diagram of the PN junction. So in the P side, away far from the depletion region. So we call it a depletion region because this is depleted from the mobile charge carriers. Okay, so this forms a depletion region where there are only immobile ions. There are no free charge carriers in this region. No free charge carriers in this region, but free charge carriers are in this region and in this region. The whole semiconductor, this whole semiconductor is electrically neutral. There is no extra positive charge or no extra negative charge, but whole semiconductor is electrically neutral. This region is neutral, this region is neutral, and this whole region together, the depletion region together is neutral. Okay, so there is a depletion region. This W is the width of the depletion region. So in the P region, this is the P region, away from the depletion region, this Fermi level is near to the valency band, this case. Okay, so and away from the depletion region to the towards the N side, the Fermi level is near to the conduction band. So how and Fermi level should be constant also. This Fermi level should be constant. So these conduction band and the valency band, they have to adjust itself so that the Fermi level should be constant, and it should also follow the concentration of the how the hole and electron concentration is varying in the semiconductor. Okay, so and in this region there is no slope. There is no slope in the conduction band as well as in the valency band, and also in this region there is no slope in the conduction band and the valence band. So this is actually the assumption that we will break in the subsequent slides when we will derive the current in a PN junction. Okay, so we are assuming that there is no slope, but we will see it later. But there is a very small slope is there in this region. But and another thing is, so here in this region, in the depletion region, there is slope in the conduction band and the valency band. So there is field that we have already discussed. There is a field because of the positive and negative ions. Okay, so this is there is a field. So if we put an electron here, it will roll down this side. So always, as we have seen, always electron flows opposite direction to the field. So we, from this Venn diagram, we can always say that the field is in this direction. Okay, so yes, this is done. So so now we come from drift and diffusion also. At the equilibrium stage, so what happens is the drift current, there will always be like as generation and recombination is always going on in a semiconductor, there will always be a diffusion, and because there is recombination, there will always be a some of diffusion also. There will be a drift also because of this concentration gradient, because of this field. There will be a drift. There will always be a drift. Okay, whenever there comes an electron at this position, it will drift down. Okay, it will drift in this direction, and whenever there is hole comes at this position, because of the field, it will feel, so it will go in this direction. Okay, so there will always be a drift current, but to balance this drift current, there will always be a diffusion current also at the same point, because of the concentration gradient. In this region there is abundance of electrons, and in this region there are abundance of holes, but there are less electrons in this region. So always electrons will flow in this direction because of the concentration gradient, but because of the field, the electrons will flow in this direction because of the inbuilt field. Okay, so there will at equilibrium, this drift component and the diffusion component balances out. Okay, drift current and diffusion current balances out at equilibrium. Yeah. Okay, and now uh, now we can find out there are some things like what is this built-in potential. We need to calculate the what is the built-in potential. How can we calculate this built-in potential is, so we know that this is the bend, this is the uh, energy band, we say energy band gap easy. Okay, this is easy. So and let us assume this is phi p, the in the difference between the Fermi level and this conduct and the valency band towards the p side. This difference is phi p, and this difference is phi n. So if we just look at this point, so what is qvbi? This is the built-in potential. Qvbi will be nothing. Qvbi will be Eg minus phi p minus phi n. This phi p is this thing, this phi n is this thing. So we can easily calculate from the concentration of the electrons and concentration of the hole. This phi p can be calculated from the doping concentration. Okay, what is the doping concentration? This phi p can be calculated, and from the this doping concentration of electrons of, or the we can say the n type, we can calculate this phi n. Okay, so this phi p and phi n can be easily calculated, that because we doped the semiconductor, we know know how much doping we have done. Okay, so from phi n, from this formula that we have already seen before. So this phi n and phi p can be calculated. So from this we can calculate the qvbi, the built-in potential. We can calculate the built-in potential. Okay, from this formula, and this can be reduced to the this one, just a simple mathematics, and finally this can be reduced to qvbi is equal to kt by q ln na nd by ni square. I think till here we covered last time. This also we have covered. Okay, so as we have seen in a semiconductor, this is a semiconductor, this is p type, this is n type. So after at equilibrium, what happens is this is the ion, this is negative impurities, negative immobile ions. These are the positive immobile ions. So there is there is a charge. How much charge is that at this position? How much charge is this at this position? This is nothing. This graph is nothing but this is q and this is x in this direction. So this is the charge density. So q and d, this is nothing. This is q and d. This is the charge density, sigma. We can say sigma. Okay, this is in the y-axis is sigma, on the x-axis is the length of the semiconductor, we can say. So this is the spatial variation of the charge density inside a semiconductor. So this q and d is the charge density at the junction towards the n side. Okay, q and d, and q and a is the charge density towards the p side. Okay, from this at this position, so this wp and wn are nothing but wp plus wn. I haven't wrote. Okay, w that we have already seen. W is the width of the depletion region. So how so wn is the extent of the width of depletion region towards the n side, and wp is the extent of the width towards the p side. Okay, so from and we know from the we know that Poisson's equation. Here from the Poisson's equation is d2v by dx square minus df by dx. Here f is the field, not the force. F is field, because we generally take E as a field, but here we have taken E as the energy. In the previous slides we have taken the EC and EV. That is the energy of the this conduction energy, okay, electron energy. Okay, we have already taken. So just give me a minute, someone wants to join. Okay. Yeah. Okay, W is W. Okay, yeah, we are this F is the field. Okay, so from this we can calculate the field. Okay, so yeah, from this df by dx is equal to sigma by epsilon. Okay, from epsilon is nothing but epsilon naught into epsilon s, the of the for the semiconductor. This is epsilon naught into epsilon s. Okay, so df by dx, from when we want to calculate the field, how field is varying inside a semiconductor. Okay, so there is nothing in this side, this is electrically neutral, this is electrically neutral, so there is no field, because there is no what to say, there is no gradient in the conduction and the valency band, so there is no field. Field is, as we have seen, at the depletion region. So we are calculating the field at the depletion region. Okay, how the charge density we have seen at the in the depletion region is qnd and qna. Okay, so we will calculate the field in this region, in the from 0 to wn, and from minus wp to 0. So for two regions we will calculate the electric field. So first let's calculate for the positive x-axis from 0 to wn. So fx is equal to 0 to wn. So this will so when you solve it, so solve it for the boundary condition. Okay, I haven't shown you this. Okay, df by dx is equal to qnd by epsilon naught epsilon s, and we will integrate it for for fx for the field from 0 to wn. So this will come, so fx will be equal to minus q nd by divided by epsilon naught epsilon s into x plus c. So c is the constant. So we have the boundary condition. We have, what is the boundary condition? Because there is no field in this region, so where the field is ending at the starting of the depletion region. So here at wn the field should be 0. So f of x is equal to 0 for x is equal to wn. Okay, so when we put this condition in this here, so we will get the c value, and c will come like this, and from here we can calculate how the field is varying, in this region, say from 0 to wn. This fx is equal to qnd divided by epsilon naught epsilon s into wn minus x. So field is varying linearly. Okay, so field is varying linearly. So okay, yes, did I made any mistake? No. Maybe. Okay, this is just a formula. You can recalculate. If there is any mistake, you can calculate it. Okay, so what is the maximum field? Maximum field will be at this junction, at when x is equal to 0. So let's put x is equal to 0. So this will be equal to q nd divided by epsilon naught epsilon s. So there will be a negative sign. Definitely there will be a negative sign. Okay, so that's what I was asking at. Okay, so there will be a negative. So because this was negative, this was negative, so when we keep it, I think it will be like this, whatever. So you can check once. Okay, so f max will be q nd divided by epsilon naught epsilon s into wn. So from for the p region, when we calculate for the p region from minus wp to w to 0, again we need to integrate. We just the same method we need to integrate, and we will find that again there will be a dependence of linear dependence of the field on there will be a linear dependence of the field. Okay, so f max for both for any region, we can calculate this field. So from both the sides we will get the f max from p side as well, from n side as well, from the p side as well. Okay, from this here we can just q by q, so q epsilon naught epsilon s, it will be gone. So nd into wn is equal to na into wp, that we have already seen. So in the last class we have seen. So if we increase the doping, so if we increase the doping of donor atoms also, which is the n type, if we increase the n type doping this side, so what will affect, how will it affect the depletion region on the n side and the p side? So okay, so if we increase the doping concentration on the n side, so wn will reduce. So if we increase this thing, wn will decrease to make it as it is. Okay, if we increase the nd, the doping concentration, so this depletion region on the n side will shrink. Okay, if we increase the doping concentration on the p side, so this depletion region on the p side will shrink. Okay, this is the takeaway message. So this is how p plus n and n plus p kind of diodes are made. So they are highly doped, so they are a kind of single side depletion layer region kind of diodes. Okay, single sided depletion region will be there only. So okay, yes, how? So this is the field. This is the field expression for okay, for 0 to wn, x is equal to 0 to wn, and this is the field expression for when you calculate the same method. This is the for minus wp to 0. Okay, so this is also negative, this is also negative. So okay, so now, so to calculate the how this we have already seen that from not seen, actually we have just drawn this band like this, like parabolic behavior. We have drawn these parabolic behavior, but how they come parabolic, that is square dependence, how they come parabolic. So we haven't talked about this thing. So how, so you can easily calculate how they are depend this is parabolic dependence. Okay, so we know that from the Poisson's equation, d2v by dx square is equal to minus df by dx. So from here you can calculate, I haven't calculated. Okay, so from fx is equal to minus dv by dx. Okay, fx is equal to minus dv by dx. So from here, from this and this, we can calculate the potential v. We can calculate the potential v. So this potential will come like this. This potential will have a square dependence on x. Okay, potential will have square dependence on x. Just give me a minute. Okay. Yes. Okay, so So this potential will have a square dependence on x. So from here we can see that this is a square dependence. This is a square dependence. Okay, and also E is nothing. This V is nothing but is equal to minus Q into E. Okay, Q into energy. This V, this potentially is minus Q into E. Okay, so this band which is E energy nothing but E, so how it will be minus of 1 by Q into V, so it is negative of just negative with the some constant multiplication. So the bands EC and EV will look like, okay, so will look like just opposite, negative of this thing, negative of this thing. So that's why this there is a square dependence of that's why the bands look like this smooth kind of nature. Okay, there is no kink anywhere in this thing. This is the ideal condition also, although. So now what we can see, okay. Uh-huh. So now we can calculate the VP, the potential at this point and the potential at this point, VP and VN. So after calculating the potential, the whole potential equation, so we can calculate VP and VN at minus WP and WN respectively. Okay, these equation will these are the values will come. So now we can calculate the QVBI. QVBI is nothing but VN plus VP. Okay, so just add these two. So this is the QVBI. And again one another thing, how so now we are going to calculate what is the depletion region width, WW. Okay, we are going to calculate that thing. So that's why we are calculating VP and VN. So also we know that W the total depletion region width is WP plus WN. Okay, so and also we have seen in the last slide that NdWn is equal to NaWp. So the this we call as areal concentration, areal areal density, not concentration, areal density, areal charge density. And from here, from these two equations, we can calculate, we can see WP and WN. Now just because there are two variables, now we just want we can replace WP and WN with these equations, and now from here we can calculate W, the total depletion region width, the total depletion region width we can calculate, and that will come out to be square root of twice of epsilon naught epsilon s divided by Q into VBI and into 1 by Na plus 1 by Nd. So these are the parameters on which Na, Nd, these are the doping concentrations on which this depletion region width depends on. Okay, if we increase the doping concentration Na and Nd, what will happen is this depletion region width will okay I might have made a mistake, I think. If we increase the doping concentration, so it should decrease actually, or I will check once because it is the inverse relation. Okay, so Na plus Nd divided by Na Nd, it should decrease. Okay, this I might have made a mistake. Okay, yes. Okay, yeah, built-in potential will increase. Built-in if we increase the doping concentration, built-in potential will increase. Yeah. Okay, and definitely if we increase the built-in potential, this depletion region width will increase. If we are going for a large band gap semiconductor like gallium nitride or zinc oxide, kind of these semiconductors, this built-in for them the built-in potential is high because of the large band gap, and therefore there will be a large higher this depletion region width. Okay, and for if we say for gallium arsenide or so the depletion region width will be lesser. Okay, yeah. So now we come on across the PN junction under forward bias. So I think from here we need to carry. This was still the last class, last tutorial session. So now let us see PN junction under forward bias. So in forward bias, what happens is when we apply positive on the P side and negative on the negative voltage on the N side. So what happens is, so at P side, if we apply positive voltage, so it will reduce the energy of the electron. So the conduction band and valency band will shift downwards because it will reduce the energy of the electrons. So this is nothing, this conduction band and valency band is nothing but the electron energy. Okay, so if we apply the negative to this to at this junction, at this point, so it will increase it, because there is negative, so it will increase the electron energy. Okay, it will increase the electron energy. So this EV and EC should shift upwards. So because it is increasing, so increasing the electron energy. So what will happen is, so this built-in potential will reduce when we apply the forward bias. So how much it will reduce is, it will reduce by the potential that we are applying across the P and N junction. Okay, so this is VBI minus VA. This potential will reduce to this built-in potential will reduce to Q times of VBI minus VA. Okay, so now this PN junction, as we have applied the bias, so this is not in the equilibrium condition. So equilibrium is distorted. So now there will be quasi Fermi levels on the N side and the P side. So the quasi Fermi level EFP is on the P side and EFN is on the N side. Okay, so there will always be when we apply the bias, there will be a distortion in the equilibrium state. So it is moved from the equilibrium state. So now when there are electrons, so the electrons on the N side, they will feel less barrier in the depletion because of the we can say the uphill, the height of the uphill is reduced from VBI to VBI minus VA. This is the height has been reduced. So there are very good chances of this electron can climb this hill, and this hole can climb this hill. Okay, so this is hill for electron, because the whole energy is increasing in this direction. Whole energy is decreasing in this direction. That you can see as a bubble in water, or water will always come upwards, so to get at the least energy state. Okay, so bubble comes up, so the same you can see the hole will always come up. Okay, so if it wants to go, when we apply a bias, so this hill will be reduced. So also this W will also reduce. W is the depletion region width will also reduce. So there are good chances of the electrons going from N region to the P region, and holes from the P region to the N region. The chances are increasing. So carriers are these carriers. So when we apply a forward bias, so the electrons are injected. We say the injection of the electrons from the N region to the P region, and injection of holes from the P region to the N region, where they are minority carriers. So electrons are minority carriers in the P region, holes are minority carrier in the N region. So at this junction, they are at this point in this region, holes are minority carriers. In this region, electrons are the minority carriers. So as we have seen, depletion region width will reduce, and potential will reduce, current will flow, because there is flow of the electrons and flow of the holes, so the current will reduce. So because of this at the injection of the electrons, so at this in this region there were some there was a kind of steady state, we can say. There were some holes. There were a fixed amount of electrons and fixed amount of holes. So but as we have applied the bias and electrons are climbing in this direction, so these are the extra electrons. These are the extra electrons here, and these are the extra holes here. So that we have already seen in the last tutorials, that delta n and delta p is nothing but these are the excess electrons and holes that are either generated or injected in the p region, and in the n region. Extra electrons in the p region, extra holes in the n region. So we have already drawn the profile from the continuity equation. We have already drawn the profile how it will look like. Okay, so there will be extra holes. So okay, let us see. So there will be extra holes, let us say delta n. So okay, so at this position there will be extra holes, say delta n, extra electrons, say delta n. So how they will decay spatially? So there the exponential decay profile that we have already seen, there will be an exponential decay profile like this. Okay, to the equilibrium value, that we have already seen, that steady state value, that we can say np naught. Np naught is nothing, the electrons in the p region. Okay, electrons in the equilibrium electron concentration in the p region. But delta n came, so extra electrons, there are extra electrons, they will decay by recombination will happen because of these extra electrons. Because as we have seen, u is nothing, u is the net recombination rate, which was Pn minus Ni square divided by P plus N plus 2Ni. Okay, so this was net recombination rate. Okay, so which was because of the if Pn is greater than Ni square, here at this position Pn is greater than Ni square, so this will they will recombine, and their profile at the steady state will be like this. At steady state, this is at the when steady state is achieved. Okay, so the excess minority carrier profile will be like this. So there is a gradient. So there is a gradient in the concentration gradient. So there will be a diffusion current. Okay, so there will be a diffusion current, and at this point in towards the n region also, there will be extra holes, extra minority carriers. Okay, so there will be a diffusion current because of this. Okay, so that we will see. Because of the concentration gradient, it will give you diffusion current. Minority carrier profile, that we seen that there will be an exponential decay profile. So we will see that, and that will give us the diffusion current. Okay, so now we will see how this will look like. Okay, just forget this part, forget this part currently. Now, so delta p in the n region. Okay, so we will just talk about which region, I will tell you. So we will talk about this region only. Now first let us this region, from here, this region. Okay, so we will talk about this region only first. We then there is same thing is happening on the other region also. Okay, delta p is the excess injected holes. excess injected holes that which were because of the applying bias applied. So how much they are, so from the Fermi level, from the like what to say, because of the applied bias there is an decrement in the VBI. Okay, from there, so how much decrement in the built-in potential was VA. So from that we can calculate the total electron concentration, total electron concentration or total hole concentration at, okay, total electron and hole concentration as at these two locations, at Wn and Wp. Okay, so we are calculating the hole carrier concentration, holes. What is the total hole concentration at this position will be given by Pn is equal to Pn naught into exponential of EVA by KT. Okay, Pn naught is nothing but Pn naught is equilibrium carrier concentration. Okay, or we can say at very far from the junction, at very far from the junction, at this point we there will be Pn naught. If it is very long diode, so at this junction it will be Pn naught. Okay, so very large at, and this Pn naught is nothing but Ni square by Nd, because this was the equilibrium carrier concentration. Just give me a minute. Okay, Pn naught is the equilibrium carrier concentration. Okay, how delta P, the excess carrier concentration is nothing but the total hole concentration at this junction, Wn. This is Wn, this point is Wn. Okay, at this junction minus Pn naught. What was the equilibrium carrier concentration? Equilibrium minority concentration was this. Okay, so this is delta P. Delta P is equal to Pn minus Pn naught, which is equal to Pn naught into exponential of EVA by KT minus 1. Okay, this is the delta P. At this is delta P. This can you see? This is the delta P. Delta P. Okay, this is delta P. And okay. Okay, leave. So another thing is delta Px. So how spatially this carrier concentration is varying? Okay, how spatially in the x direction, this concentration, this profile we need to find. So we have, from the continuity equation we have already seen that this is the exponential dependence, and how it is depending exponentially, which is the initial concentration at this point into exponential of minus of x minus Wn by Lp. Lp is nothing but the diffusion length of the holes. Lp is diffusion length of holes. Okay, so this is exponential decay profile. This is the exponential decay profile. From delta Px is equal to Pn naught into exponential of EVA by KT minus 1, and this exponential spatial profile. So we know that Jp is nothing. Jp is the diffusion current. So we will calculate the diffusion current. So diffusion current is nothing but Q times Q into dP into delta of Px divided by del x. So Px is the concentration, spatial, how concentration of the holes is varying with the with x. Okay, so So from here we will we are given with d delta p, the x variation. So by when we differentiate an exponential function, we will again get an exponential function. Okay, so after differentiating jpx is equal to this thing, so we will get an x again exponential function. This lp will when we differentiate it, 1 by lp will come out. Okay, so now this is the current that we got, that diffusion current, because of the minority carrier injection on the n side. Okay, this is diffusion current due to diffusion current due to minority carriers, minority holes on the n side. Okay, so and this will depend on the concentration of the doping concentration dp. Okay, this will depend on the whole concentration. Okay, on the whole concentration. So whole concentration I am saying, not dp, no, dp is the diffusion coefficient actually. I was saying another thing I was saying actually, which is pn naught ni square by nd. Okay, so this pn naught, if we see this pn naught, just minute, this pn naught is equal to ni square by nd. Okay, I got confused with dp and nd. So this constant, this whole current whole current in the n region is depending on the concentration of the doping concentration of electrons. Okay, so the whole current, ho whole current, which is whole current, is depending on the concentration of the dopant concentration of the electrons, or say so n type doping. So it is not related to the p dopant, but it is depending on the n type dopant. What is the doping density of the n in the n region. Okay, so yeah, and this was the thing. So just remember that thing, how the electron and this minority carrier current is depending on which parameters. Okay, so this is the log plot actually. This is the log plot. Okay, so there is very actually, what to say, there is a small change in the majority carrier concentration, so that that is actually equal if we in the real scale. So delta n is equal to delta p only. Okay, so delta n is equal to delta p only, kind of. So but this on a real scale that we can see, on a real scale only that we can see. Okay, on a real scale, but in the log scale we cannot see, because this is a relative, 10 raised to power, just say n type concentration is 10 raised to power 16, and carrier injection at that point is also around 10 raised to power 17, say. So there is very small change. There is very small, but that change can be easily seen in the relative concentration of the minority carriers. Okay, so this is the real scale and this is the log scale. This is the like in linear scale, this is the log scale. Okay, and now if we want to calculate the total current in a PN junction, so we know that there is current, there is a diffusion current. So that we have already seen. So that because of the this profile of the minority carriers, this red profile that you can see here, this is exponential, this is exponential. Okay, so after differentiation the current will also be in uh, in exponential. Okay, the differentiation of exponential is again exponential. So the current will come in the minority carrier diffusion current will come like this. Okay, that is also exponential. And we are assuming our diode, these neutral regions are long enough, then this diffusion current comes to at this in end. So that is this diffusion, this P comes to P is equal to P naught, P n naught, this delta n comes to equal to approximately equals to 0 before ending the diode, before like that quasi neutral region, that quasi, we call it this a quasi neutral region, quasi neutral. So till this point it should end. Okay, we are and this is the long diode condition. Okay, we call it long diode condition. So this is the diffusion minority carrier diffusion current. So which is because of the holes, minority carriers holes in P region, in N region actually. Okay, and now the same current, this because of the electrons will be on the N side, no, on the P side because of the minority electrons. Okay, because of the minorities electrons, minority carriers, the same profile. I am not saying the current will be equal, but the same profile will be same. Okay, this is the exponential decay profile. This is the minority carrier diffusion current. Okay, at this junction, just see, at this junction and at this junction there is a current. Okay, but as we have seen, so this is the our PN junction. Okay, so at this is minus WP and this is WN. So at this point there is no concentration gradient, as we are assuming, and no recombination in the depletion region, we are assuming that thing. Okay, so there is no recombination in the depletion region, so there is no concentration gradient. So there is no concentration gradient, but there is current. That is because of the drift. Okay, that is because of the drift, because of the uh, okay, what to say is yeah, there, because of the there is current, and what should I say, I may not be correct at this point, but there is current which which is not because of the diffusion of the carriers. Okay, because there is no concentration gradient in this region. So what will happen is, so this current will be constant in this region. So in also we know that the total current will always be same in the whole PN junction, or whole semiconductor device. The total current will be same. Okay, this is the current due to the electrons, this is the current due to the holes, minority carrier holes. So the total current at these locations JP and JN, how much will it be, how much will it will be? So this is the J total current. Okay, this is the J total current. So this total current will always be, if this is in the depletion region, it will be same in the quasi neutral region also, in the quasi neutral region also. Okay, so this is the diffusion current, but the total current is this thing. So what is the difference? The difference is the drift current. Okay, this difference between the total current and the minority diffusion current is the drift current. This is drift current, and the difference, this is the drift current. Okay, so these are the two drift currents, but as we have already we have seen that during our assumptions I said that there is no there is no field in the quasi neutral regions. Okay, but there is very small uh, field, which is because of that there is the this drift current. Okay, and this drift current is so high, very small electric field, because of the very small, because the N and P concentration, this drift current is not because of the minority carriers, but this is because of the majority carrier concentration. Okay, this drift is because of the, in this region N region, this is the because of the N electrons, and in this region this is because of the holes. Okay, so the N and P concentration is high, so there is the drift current. So with a very small application of the field, this drift current will be very high. Okay, so uh, there will be a drift current. Okay, so now we have seen that this is the total current. Total current is this thing. When we add these two currents at the junctions at JP at JP at WN, JN at minus WP. Okay, JN at minus WP. When we add these two currents, there will be total current that we have seen. Okay, this is the total current, which is due to electrons plus holes. Okay, so this is the reduced equation that when we arrange these things, okay, this will be an exponential dependence. Okay, this will be an exponentially depending. So this parameter, this is nothing but the J naught. Okay, which is a constant, which depends on the doping concentration and all these things, because these will depend on, so that we will see. And we also say this is the reverse bias current, that we will see. Okay, so total current is J is equal to, which is exponential dependence on the applied voltage. J is equal to J naught exponential of QVA by KT minus N. So how it will depend exponential dependence? So I will add one slide once. Okay, so I am assuming there is no, okay. Okay, so how this current will look like, the exponential, the graph of this current will be. So this is the voltage that we are applying, V. Okay, so initially the current will be very less. It is exponential, J is equal to J naught exponential of QVA by KT, VA by KT minus 1. Okay, so initially the current will be very less. Okay, so after turn on, it will vary exponentially. Okay, the current will sudden rise will be there in the current. So this is how the current depends. This J is depending on the voltage that we are applying on in the PN junction current is very. Okay, so now let us see. Wait. Okay, now let us see how how a reverse bias PN junction is behaves. Okay, so in reverse bias, what happens is when we apply a positive at this junction. Okay, no. When we apply, okay, this is PN junction. When we apply a negative at this junction and positive at this junction, what will happen is it will increase this negative will increase the energy of the electron, so the conduction band and the valency band will move up, and this positive will decrease the electron energy. So this conduction and valence band move down, so it will create a more the depletion region width. This depletion region width will increase, because this will increase this the built-in potential also. This built-in field QVBI will increase to QVBI plus this VA, mode of VA. Okay, or reverse by in reverse bias we can call it VR. Okay, this VBI will change to QVBI plus VR. Okay, so what will happen is this okay, JN okay, so if you see, whenever an electron comes at this point from the minority carrier, so electrons are the minority carrier in this side. Whenever an electron comes at this position, so because of the large electric field, it will go down. It will like it is kind of a vacuum cleaner. Okay, so vacuum cleaner, it sucks the air, so it is like that only, so it sucks the particles now. So it is the vacuum cleaner for these electrons at this position. It is vacuum cleaner for the holes at this position. So the holes will immediately swept away. The electrons will immediately swept away from this point. So at this point, the minority carriers, there will be no minority carriers at this position, because of the very high electric field built in this electric field at this position, reverse electric field, or we can say. Okay, so because of that, these will be swept away. At this position, the electron concentration will be almost zero. Okay, at this position the whole concentration will be zero. So this graph shows the electron and hole concentrations at the junctions, at the depletion region, or at minus Wn and minus W, at minus of this Wp, and this is Wn. Okay, this is nothing but minus Wp, and this is plus Wn. Okay, at these locations, the minority carrier concentration will be zero. This is what shown in this graph. Okay, so this will vary exponentially. Okay, so this concentration, this due to this electric this diffusion, because of this concentration gradient, there will be a flow of current. So that flow of the current will be because of the diffusion from the higher concentration to the lower concentration. These are nothing but the minority carrier concentration. The current will be a very small current will be there, because of the minorities, because they are very less in number already. But so this because the electrons are moving this side, so the current will be in this direction, Jn. Okay, so and holes are moving in this direction, the whole current will be also be in this negative x direction. Okay, so the total current will be nothing but the diffusion current that we have already calculated for the this forward bias, which is that constant part. This is J naught, which is equal to J naught equal to Q times dP by LP, or Pn naught plus Dn by Ln Np naught. This is the current, that reverse saturation current we say. Okay, reverse saturation current, or we can call it as leakage current that we never want in our device. Okay, this should be as less as possible, because PN junction, a diode works for as a rectifier. A rectifier is nothing but, rectifier is when we work as a rectifier, so a diode, so the current in one direction the current should increase, and in the another direction the current should be zero, kind of. Okay, so the current should be zero, but because this there is a some current J naught, and this J naught is nothing but this reverse saturation current. Okay, this is constant. Okay, we can see this is constant, and which depends on the on ND, which is the doping concentration, Na doping concentration. If we increase the doping concentration, what happens? What will happen? Okay, if we increase the doping concentration Na and Nd, this we can say this okay this yeah, depletion region width will increase, or we can say this potential barrier, this VBI will increase, and okay, just a minute, VBI will increase, so this J naught will decrease. Okay, this J, or we can directly from the formula also we can directly see, and this PN naught depends on Ni square by Nd, and NP naught depends on Ni square by Na. So from here it is inversely relating. Okay, inversely relating, so J naught will decrease. Just a minute, I will admit someone so who is waiting. Okay, just a minute. Okay, so J naught will decrease. And in another thing what we were looking at is, if, okay, so this also depends on the Ni, and Ni, okay, okay, I'm unable to clear it. So this Ni depends on this band gap Eg. Okay, more is the band gap and lesser will be Ni. If Eg increases, this implies that Ni will decrease. The intrinsic carrier concentration with decreases with increasing in the band gap. Okay, so if we increase the band gap, Ni decreases, so the this leakage current decreases. This reverse saturation current will decrease after when we are going for the large band gap semiconductors like gallium nitride, zinc oxide, or silicon carbide, kind of the which are used for the high power electronics, because we need very less leakage current in that case. Okay, so let's move further. Okay, I just keep. Okay, so now I haven't made the slides, but I will write on the board. Okay, so let me see which things needs to be covered further. Yeah, okay, so now we have seen that there is a reverse saturation current because of this this is the reverse saturation current. Okay, this is the reverse saturation current that we have seen, but this is the ideal condition when we have assumed there is no recombination in this region. Okay, but in real devices what happens is the, okay, but in But in real devices, what happens is there is a there is always generation and recombination in the in this region also. So let us assume this is the PN junction diode, and this is the PN junction. So this is the depletion region. Okay, this is the depletion region, and in real device there are some traps. There are some traps in the in in the semiconductor. So there are traps in this region also, in this region also, but they don't affect that much to the to the current, because we are looking for in this region. So there is recombination also. Okay, when an electron is moving from at this point to this point, so it will be recombining, it might be recombining. Okay, through the traps that we have seen, the total recombination rate u is equal to 1 by tau into Pn minus Ni square divided by P plus N plus Ni. Okay, twice of Ni. Okay, this is the total recombination rate. So because of this there are because of this there will be an extra current, because of there will be an recombination current, because whatever diffusion current that we have calculated, because these electrons from here at this point. Okay, from this point we have calculated the diffusion current due to because of the minorities. But what about the current that is already because of this recombination? Okay, that we haven't seen. So the recombination, we need to include this recombination current also in the forward bias case. Okay, in the forward bias case. Okay, so how it will be, so net recombination rate is this thing. So as we have already seen one more thing, that these recombination sites will be most active at when these ET means the trap state is near to the intrinsic Fermi level. Okay, near to the Fermi level, which is equal to EI. Okay, ET is equal to EI, and okay, just give me 2 minutes. Forward bias. Okay. Okay. Okay, so they will be most active at this point. So the maximum recombination rate that we can calculate is the, like, when recombination is one thing we are also assuming P concentration of P and N, because at this position P and N is much greater than much P or N, whatever P, either P or N, in the N side junction, N side it is N, and P side it is P. P and N are very greater than Ni. Okay, so in the respective regions. Okay, so so from this maximum recombination rate, this maximum recombination rate can be equal to 1 by tau into we can neglect this Ni from here, so it will be Pn divided by, so for the n region we can neglect p. Okay, we can neglect p for the n region, and ni will all, this is the intrinsic carrier concentration, this is minority carrier concentration. As compared to n, they are negligible. Okay, this is divided by n. Okay, so this comes out to be p divided by tau. This comes out to be p divided by tau, and p. Okay, okay, just I might have made a mistake, maybe. Just give me a minute, bus. Oh, okay. I just made a mistake. We cannot ignore this ni. Yeah, we cannot ignore this ni because this is ni square, not ni. Okay, we cannot ignore. So that's why I was wondering how can I make it. Okay, so actually how it will be, so pn, so in this case the pn, the p into n. Okay, pn is equal to nothing but p naught n naught. Okay, this is equal to pn will be equal to in at equilibrium, pn is equal to ni square. Okay, at equilibrium, but the equilibrium is distorted here, so the pn will be equal to ni square, and how much the voltage that we have applied. Okay, how much the voltage exponential dependence of the qva by kt, qva by kt. This pn is equal to ni square into exponential of qva by kt. So the total recombination rate will be reduced to this pn, this nip, when we replace this pn with ni square into this exponential of qva by kt, so it will be reduced to ni square common out. Okay, q exponential of qva, exponential of qva by kt minus 1. Okay, this is minus 1 divided by p plus n plus 2ni. So here we can neglect this p and 2ni, so it will be n. No, here it will be, okay, and I don't know which. Okay, okay, yes, 2ni. Okay, I'm really sorry, I just did this thing. Okay, wait a minute, someone is coming. Okay, so okay, now okay, let me start it in the next slide itself. Okay, so actually this is the depletion region. I did some mistake. Okay, so in the depletion region itself, so we are okay, I made this more steeper, but this is in the forward region. So when there are traps, so j total will be equal to j diffusion due to minority carrier, plus that we have already seen, plus the due to the j recombination. So J recombination, we are calculating the recombination current, J recombination. That is due to, because we have calculated the diffusion current from this point at this point, but we haven't calculated the recombination current, the current due to the electrons which are the majority carriers in this region. So due to the recombination which are recombining at this, because we have assumed that there is no recombination in the depletion region. Okay, so which that is what we are calculating. So this will be okay, that we have seen that u is equal to in the last slide 1 by tau into ni square into e raised to power qva by kt minus 1 divided by, so we were confusing about what we should do about the p plus n plus 2ni. Okay, so p okay, p into n is equal to p into n is equal to nothing but ni square, which is p into n is equal to ni square into exponential e raised to power qva by kt. Okay, so but p and n, whatever we take it is okay. So at this position p will be equal to, in the depletion region, actually I am a bit confused in this, how this concentration will vary, because this is the depletion region, how this concentration will vary. Okay, so okay, what I have seen is okay, so but it is given, this p and n concentration is given as p is equal to n is equal to ni exponential of qva by 2 kt. Sorry about that. So it is given by this formula. Okay, so at in okay, I think someone has any doubt. Actually, Shivangi, actually we are not allowed to solve the assignment 6 currently, because I think that assignment is, you need to submit that assignment. Okay, so when the deadline will be passed, we will solve that assignment, because
Okay, sir.
yeah, because if I'll solve the assignment in this class itself, so how they will mark? Okay, how we will mark you in the exams? Okay, so we
Yes,
cannot
sir.
solve the assignment now. Okay,
Okay, sir.
yeah. So from for assignment 5th, or you can upload the picture of the question, if from 4th 5th, these assignments you have any doubt, we can solve that. Okay, so not
Okay, sir.
from the 6th.
Sir, where to upload that questions?
Okay, I need to check once. You can just tell me the question number if you have, so I will check once. Are you currently solving the assignment?
Yes, sir.
For fifth, fourth assignment, second, third, fourth assignment. Do you have any doubt?
Yes, sir. But right now I don't have my questions. So,
Okay, okay. In the next tutorial, you can ask them.
okay, sir.
Yeah,
Okay.
in the next tutorial, you can ask. Okay, so
Okay.
and maybe in the next tutorial, I will try to solve the all the assignment questions only. Okay,
Okay, okay.
so that
That
will be
will be
much
okay,
better.
sir.
From second assignment till fourth or fifth assignment, I will take all the questions.
Okay.
That will be much better.
Okay. Okay. So that answer I will get on this session only, 6 to 8 live session only,
Yeah, 6
or
to
we can
8.
get through mail also.
Huh? Yes.
So can we get that answers on the mail or on our portal or
Actually, I'm
because
not.
if I will unable to join this session 6 to 8, then how I
So
can get the
you can
solutions?
watch the recording then. Actually, I don't know, or I will upload the notes also.
Okay, that will be fine, sir, because daily to attend 6 to 8 session is not possible for me.
Hmm.
But I have many doubts, so I am unable to resolve that doubts on my own basis. So I need
Okay.
help to solve the numericals.
Okay, okay. So, what you can do is there is a problem solving. There is chat. I think there is chat. It is given, so you can ask your questions there. So we can of all the like TAs can have a look and can answer your question. There is no problem.
Okay.
Yeah, there is. I think
Okay.
chat link is given. Maybe I don't
Yes,
know,
sir,
but
chat is given.
yeah, one chat link is given. Okay, so that you can see.
Okay, thank you, sir.
Yeah. So from here, what you can see is you can calculate the total this P is equal to N is equal to Ni QVA QVA by 2 kT. So this total recombination U is equal to 1 by tau into Ni square into EQVA by KT QVA by KT minus 1 divided by divided by divided by twice of Ni P plus N. This P plus N will form twice of Ni into uh, twice of Ni into exponential of E of QVA by KT. Okay, this will be so Ni will cancel out, this one Ni will be cancelled out. So so it will be, this will be equal to u will be directly proportional to, u will be also equal to 1 by tau into Ni, which is Ni, this can be u is equal to 2 tau 1 by 2 tau Ni e raised to power QVA by KT minus 1 divided by okay, exponential of QVA by 2 kT. Okay, okay, I will write again this thing. I'll write in the next slide. Okay, yeah, okay. So u, that is the total recombination rate, will be directly proportional to 1 by 2 tau into which is this is Ni into uh, exponential of uh, QVA, which is QVA by KT minus 1 divided by, this is divided by uh, E QVA divided by 2 kT, twice of KT. Okay, so in this case when we increase the voltage, this v this this exponential term will rise very fast, and as compared to this exponential term, this one will be negligible, so we can ignore for the higher voltages. So this one we can ignore the higher voltage. So u, the total recombination rate, will be directly proportional to Ni divided by 2 tau, and which is equal to into exponential of uh, when we subtract this QVA by 2 kt, exponential of QVA by 2 kt. Okay, so this is the recombination rate. So the current, this recombination current, J recombination, will be directly proportional to what, this Ni divided by 2 tau exponential of QVA by 2 kt. Okay, so this will be this J recombination will be this, which is also a exponential function of the applied voltage. Okay, but in that, in J diffusion, J diffusion is nothing but J diffusion was J naught into exponential of QVA by KT. So but in this case, in recombination current, this is 2, this constant, this is 2. So but there is nothing, there is one only. So this is the eta. It is known, we call it as ideality factor. Okay, ideality factor. Okay, so because how much this your diode is behaving towards the ideal nature, or how much this recombination current is dominating in the PN junction current, so that is given by the ideality factor. This can vary, this ideality factor can vary, can from 1 to say 2, 3, 4, 5, 6, 7, 8. So more towards the 1, this eta, when we measure the current, in a real diode, the I, when we take the JV curve, IV curve, so when we take the IV curve, so it should be like this only, okay. But if it is not behaving like this, so how much, so we fit that for the eta. Okay, we fit this curve for eta and we calculate the ideality factor. So in that, so how much the this which current is dominating, so diffusion current is dominating or the recombination current is dominating, so in which region these are dominating, for the higher voltages, for the lower voltages, from these we can see how much ideal our diode is. Okay, so more towards the one, the more the ideal diode is, more towards the more greater the value of this eta, the ideality factor, so it is not reliable. Okay, not reliable, we cannot say it is not cup of our tea, because okay. So in the next section we will see, so this was the recombination current. Okay, so okay, yeah. So now let us come on the next section. So now in so also what we have seen is in reverse bias. Okay, in reverse bias, when we calculate the recombination current also, that we no, not the diffusion current, J diffusion, did as I already told, J diffusion was calculated in this direction, from this direction, but there was no inclusion of this this region. So so okay, there is so what about the generation? So this is the a reverse current, a reverse we can say. So if there is a generation of the charge carriers, so that was not included in this diffusion current. Okay, so if the current is generated, and that as soon as it is generated it is swept away, as soon as it is generated it is swept away. Okay, so we haven't included this generation current. Okay, as soon as charges are generated, they are swept away because of the high electric field in this depletion region, which is due to the reverse bias. Okay, so we will calculate that j generation. Okay, j generation. So j generation, so that for that we need to first see how this total recombination rate u is behaving in the reverse bias case. Okay, u was 1 by tau into p n minus ni square divided by p plus n plus 2 ni. Okay, so this was given. So in reverse bias case, we know at these junctions, so the charge carrier concentration is very low, there is nothing. So in this case also, here the charge carrier concentration is very less, because there is no charge carrier in case of the reverse bias. So p and n is very less than ni. Okay, and p n is very less than ni square also in reverse bias case. So this p n can be neglected in this case. So u is equal to 1 by tau into minus of ni square divided by p and n can be neglected in this case, so divided by 2ni. Okay, so this ni will be cancelled out, so it will be u is equal to minus of ni divided by 2 tau. Okay, so this is this will give the net generation. This is the net generation of the charge carriers. Okay, this will be the generation of the charge carriers. So it will give the generation current. So this, okay, so one more thing. Huh. Okay, so just okay. This will give the generation current. So the total current J generation will be given by we already have, what we have is, we have total generation rate u is equal to minus n by 2 tau. So okay, we have net generation rate. How much the current will be? Current is nothing but the q multiplied by the charge carriers which are generated. Okay, so q into the total charge carrier generation. Okay, total charge carrier generation will be nothing but the integration of the generation what should we say, the total charges, and which is integration of the with the time, or total okay, which is integration. Okay, should I should go to the okay, total charge is generated in where in this region. Okay, how much is the total charge? This is the generation rate. How much is the total charge generation generated in this region is when we multiply this with the w. Okay, w is nothing but the depletion region width. Okay, this is u into q into w, which it will give us the total charges which are generated in this region. Okay, for when we integrate this u into dx to for where from 0 to w or minus wn to plus minus wp to wn. Okay, j generation is equal to q into uh, q into ni. We have calculated the magnitude of minus of ni will be nothing, this ni, this we are taking the mode. Okay, q into ni divided by 2 tau 2 tau into w. Okay, into w, this will give us the total generation current. Okay, so okay, so this depends on, so j total, j reverse bias current is equal to minus of j naught minus of this j generation current. Okay, which is equal to minus of q ni divided by 2 tau into w. Okay, so this is the reverse saturation current. But j naught, here j naught is constant, that we have already seen, j naught is constant. But this reverse saturation current depends on ni. Okay, this ni, this generation current depends on ni, and w is nothing but that depletion region width, and this w depletion region width depends on the applied voltage. As we increase the reverse bias voltage, this w increases. Okay, we are increases, w increases. Okay, so this w increases when we increase the reverse bias voltage. Okay, so okay, shift plus n, can we, okay, so in this case what will happen is, okay, so in this case what will happen is, so this let us see, so this is the graph for the this is j, this is v, and in the forward bias this will go like this. So in the reverse bias what will happen is, so it will slightly increase with the application of the reverse bias voltage, not that much, not, don't go for the scale. So it will slightly increase and then will go like breakdown voltage. So so because of when we increase the va, this is vr, this reverse voltage we increase, the depletion region width w increases, and as we have seen here, so this generation current, j generation is equal to nothing but q ni divided by 2 tau into w. Okay, this w increases with increase in the vr, so it is varying linearly, this generation current is varying linearly, so it will slightly increasing with the application of the reverse voltage. Okay, and another thing is, it also depends on the ni. Okay, so this ni, and this ni depends on the band gap eg of the semiconductor. Okay, if eg increases, this ni decreases. Okay, this ni decreases, and this generation current will also decrease with increasing in eg. Okay, if for large band gap semiconductors, wide band gap semiconductors, this ni decreases, so the reverse leakage current decreases, this leakage current decreases. Okay, yes, and Okay, so now what we can see is how what are the, like, we have done this PN junction. So where this PN junction diodes or PN junction is come into picture for the semiconductor devices. Okay, so there are almost all the devices, whatever you read, whatever you see, so all there is a junction between the uh, like metal semiconductor, or that we haven't seen till now, that PN junction, that Schottky junction, that we will see in the next session. So what happens is, so how how these PN uh, junction is used in the semiconductor devices. So it is not only the diode. So okay, so I will show you how in the diode. So this is the characteristics of the these are the this is the characteristic of the PN junction diode. Okay, PN junction, this is the voltage, applied voltage, and this is the current. So in the reverse bias, when we apply too much of the voltage, so it will break down. So there are some reasons for the breakdown. So uh, uh, due to very high electric field, there is a breakdown. Okay, so 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 when we apply the forward bias, so it is allowing the current flow of the current after a certain voltage, which is known as the threshold voltage, VTH. Okay, which is approximately equal to the band gap. Okay, approximately, or can be larger also, which is almost approximately equal to the band gap of the semiconductor. Okay, so easy when we apply the not the band gaps of the semiconductor, sorry, this is the this is equal to the built-in potential, VBI, actually VBI, that is nothing but this is the VBI, and this VBI depends on the doping concentration, Na and Nd. Okay, so this threshold voltage indirectly depends on the doping of the semiconductor on the each side, Na and Nd. Okay, so this allows the flow of the current in positive, when we apply the positive voltage. Okay, so and but blocks the current in the other direction up to certain extent, Okay, so this can be used to for the in the circuits where we need flow of the current in single direction only. So we want to block the reverse flow of the current. So this act as a rectifier. Okay, this PN junction diode act as a rectifier, and this can be used in such devices, in such applications. Okay, where we want only flow of the current in uh, only one direction. Okay, so this is the region, this is the first quadrant where we want to use this device, we want to use this device in this region only. Okay, this is the rectifier. And in another case, this is the okay huh so next device that we can this can be used, this PN junction can be used is in the LEDs, is being used is in the LEDs. So LEDs are okay, this is the PN junction. Okay, so when we apply the field, when we apply positive bias, okay, this is the P region. Okay, yeah, this is the p region and this is the n region. When we apply the field, what will happen is electrons will go in this direction, holes will go in this direction, but in this region, electrons and holes are crossing each other. Okay, they will encounter each other in this region, in the depletion region. They will encounter each other. So they will recombine. Electrons will recombine with the holes, and when they will recombine, direct recombination, from band to band recombination, from conduction band to the valency band, the recombination will happen. So what will happen is there will be a generation of light. So how much what is the like wavelength of the light? Wavelength will be equal to the Eg. Eg is equal to hc by lambda. This wavelength lambda will be corresponding to the band gap of the semiconductor. Okay, so when we forward bias this PN junction diode is can be used as an LED. So whatever you see in your homes, these are based on the PN junction. Okay, so these are based on the PN junction. But there are this is just a basic principle. There are so many other layers also which block the flow of the electron till here. Okay, so we make this as a this light should not be absorbed in this region and in this region, so because it is generating the electron hc by lambda. Okay, but again this light can be absorbed in this region and excite an electron from here to here again. So this is which we do not want, because this is of no use, because it is generating, and that electron can again recombine through the non-radiative recombinations. So because there are traps, so when these electrons going from the n region to the p region, and these holes from the p region to the n region, they encounter each other at the depletion region. Okay, this depletion region, when they encounter, they recombine, and when they recombine, they may recombination can be radiative and can be non-radiative. Okay, non-radiative. Okay, this recombination can be radiative and non-radiative. When they recombine radiatively, they emit a photon of the energy corresponding to the band gap, which is the light. Okay, when they recombine non-radiatively, they recombine through the traps. Okay, they recombine through the traps and lose the energy in the lattice vibrations as a phonons. Okay, that we do not want. This is the just a basic principle of the LEDs. Okay, and the last one, just I am showing you, is this is not the last one, but I am just giving you the solar cell. How does a solar cell works? Okay, solar cell is also a PN junction diode only. So this is a PN junction diode. Okay, so a solar cell is what is a device which converts light energy. Okay, when light energy falls on a diode, PN junction diode, it excites an electron from the valence band to the conduction band. Okay, so it falls, and electron and holes are separated because of the built-in electric field at this position. Holes will feel a force towards this direction, electrons will feel a force towards this direction, and these holes and electrons are collected to the respective electrodes. Okay, giving rise to a current when we connect these to the external load. Okay, these are connected with the load, so there will be a flow of the electrons and holes in the circuit. So Okay, so these electrons and holes are separated just because of the built-in electric field at the PN junction, which is at the depletion region. Okay, so when we see a diode equation, which is this, okay, which is this, okay, this is the diode in the forward bias. So or we can see can also say this is a kind of photodetector, because when light falls on it, it generates the electricity. So it is giving us a signal that light falls on a falling light is falling on a diode on this device. So when you want to see when there is some radiation or not, which we cannot see, like wide bandgap semiconductors or so. So if you are want to check whether there is a UV light or not, what will you see? But how will you check that? Okay, we cannot see the UV light, but this is a photodiode, which is the band gap Eg is say around 3.4 electron volts. Okay, 3.4 electron volts. So this can sense the UV light. I don't know how much will be the wavelength, say 350 nanometer, that we can calculate easily. 3 for the 350 nanometer wavelength, what is the corresponding band gap that we can calculate easily? 1240 divided by 1240 divided by 350. Okay, we can calculate easily. So when light falls this wavelength, 350 nanometer, okay, so it will generate electrons and holes. So they will be swept away and will give rise to a current. Okay, so we can say that there is an UV light outside. Okay, so there is UV light. And another thing is, so when UV light falls, so this there will be current. So the current will be in which direction? So electrons will be go in this direction, the current will be in this direction. Okay, holes will go in this direction and the current will be in this direction because of holes also. Okay, so at when under the dark conditions there is no current, almost zero current at this V is equal to 0. But when light falls, there will be a certain current. Okay, there will be some current, and that will be like this. Okay, so at 0 voltage also there will be some current, and these are we call it ISH, we can say I because of the IPH, because of the photon falling on this thing. Okay, or uh, okay, that's it in this case. And the same principle is for the solar cell also. Okay, so I think we have covered the devices that which are because of which uses the PN junction. Okay, where PN junction is there in the devices. So which are the LEDs, photodetectors, solar cells, and and rectifiers. Okay, so today we can end the session here itself because it's 8 o'clock already. So thank you and have a nice day. If you have any doubts, you can ask me now. Do you have any doubts?